So I have to prove whether this set is compact. Okay, so you can try this problem first. So the set this minus root 2 comma root 2 intersection Q is closed and bounded but not compact. So take 1 or 2 minutes and try to see whether you can solve. Can you give me an open cover of this set? This set is closed, right?
Yes, sir.
This is closed and it's also bounded. Nothing to see. So can you please give me an open cover? So means tell me first, is it compact?
No, sir.
Okay, so can you give me an open cover? This is closed and bounded. Okay.
Sir, I did prove by contradiction method.
Uh, what is your argument?
Suppose it is compact in Q.
Compact.
Then, yes, sir, then it should be compact in R. We have a theorem.
It should be compact in R.
Yes, sir.
Yes, yes, yes. Compact in R. Is it for any subspaces or we need some closeness over this subspace? I don't think it is. I think it is for any space. Okay, it's fine.
Yes, sir.
Like it's correct. Now, can you give an open cover in a different way, like without using this result? It is also, I think, fairly easy. Minus so minus root 2. Let me take as minus root 2 plus 1 by n comma root 2 intersection q. So this will be again an open cover, right? Is it? It will be open cover of this set in Q.
Yes, sir.
Anyway, anyway, so it is fairly easy and okay. So now suppose for the second problem, suppose you have a function f from 0 1 open interval to r. It is continuous, monotone, and bounded. You have to prove that it is uniformly continuous. Okay. So which argument do you have for uniform continuity in terms of compact means in terms of compact spaces or using these compact sets? You have a function f from from say if defined in a compact metric space is uniformly continuous, right?
Yes, sir.
Or yeah, or any function defined in say 0, 1 to R if it is contests a continuous function R is uniformly continuous. Because this is a compact set. As a compact continuous function on a compact set is uniformly continuous. So can you relate this problem? Means using these three conditions like monotone and bounded. So you have to use these arguments, monotonicity and boundedness, to come up with some situation where you can give some arguments that f is uniformly continuous. Can you please take 5 minutes to try?
Yes, sir.
Yeah, sure.
So,
Yes.
sir, in which, by monotone and bounded, we can prove that every sequence in 0, 1 has a convergent subsequence that converges in 0, 1.
Every sequence in 0, 1. Which
Has a
sequence? From where?
conver- every sequence in 0, 1
Xn. Say Xn in 0, 1. Then
has a convergent subsequence
as
that
a
converges in 1.
convergent subsequence convergent in 0, 1.
Yes, sir.
Then how?
Then, sir, every open cover has a Lebesgue number.
Every open cover has a Lebesgue number. But you need this set to be compact, right? This is not compact. When you say a set has a compact has a Lebesgue number, you need the set need to be compact, right? Using compactness means using this compact metric space kind of things, you can say that space has a Lebesgue number. Means it's also again this Lebesgue number depends on your given cover, right? For an open cover, you can find out some Lebesgue number. So now tell me how do you find such a Lebesgue number? Yes. Tell me first what is your argument? Means for any sequence has a convergent subsequence here. Means have you
So,
take
as we have a theorem,
which theorem?
so that every cover, every open cover has a Lebesgue number if every sequence in that set has a convergent subsequence.
Every sequence has a convergent subsequence. Then it has
Yes,
a
sir. Yes,
Lebesgue
sir.
number. And using this convergent subsequence and where does it converge?
Converging in that set, sir.
But what about this sequence? This is belongs to 0, 1, right? Say n greater than equal to 2, or in fact you can take 1 by n plus 1. This is the sequence. Say n equal to 1 to infinity. This is a sequence in 0, 1, right? Then what will be your convergent subsequence? Sanjuwala?
Hello, sir.
Yes. Who is
So,
it?
so suppose two sequence, take two sequence A n and B n in
A
0, 1
AN and BN.
in
Yes.
0, 1.
Yes. Then yes, Piyush. Then
Yes, sir, yes. As f is continuous,
if is
then
continuous.
FAN converts to FA. Suppose AN converges to A and BN converges to B.
FAN converges to FA. Okay. You are also taking AN converges to A and BN converges to B, right?
Yes, sir.
So FAN converges to FA and ABN converges to
F of
FB.
B.
Fine. Fine. Then
And if A and minus B less than A minus B approaches to 0, then we have to prove that FAN minus FBN approaches to 0.
A minus B approaches to 0 means these are
Yes,
constant number, right?
yes, sir.
There has a difference. So either they will be 0 or they are non-zero.
Yes, sir.
So there is nothing that you are taking. So first of all, you have chosen two sequences and you are saying whenever they converge to some A and some B, these are constant, right? So their difference should be either 0 means they should be either same or their difference should be non-zero.
Yes,
A
sir.
sequence can approach, okay,
Yes,
but
yes.
two numbers cannot approach. Then any other? Okay, so first of all, can you please, okay, let me give you some more hints. Can you use something on boundedness? So let me tell you, every non-empty subset, bounded subset of R. So which in what kind of information do you know about this kind of sets? Okay, so let me uh, call you, tell you precisely. I shall erase this one. Okay, so your function f is bounded, right? So this implies this set f0, 01 is bounded. Also, it is non-empty. It is bounded and non-empty. What does completeness property of R say it? So this is subset of R, right? F is a function from 0, 1 to R. So every bounded subset of R means every subset of R or every non-empty subset of R which is bounded above has a what?
Supremum.
Supremum, yes. Supremum. And since it is also bounded below, it has an infimum, right?
Yes, sir.
Yeah. So now take supremum of F01 to be capital M and infimum of F01 to be small m. You also have something more, some more information about this capital M and small m. Those are limit points, right? Limit points of what? You can say image of F. And this is an A. So M and N or capital M and small m are limit points of image of F. Fine. Actually, our aim is to extend the function Okay, so our aim is, see, the function is given continuous in 0 and 1, right? 0, 1 open interval. Our aim is to extend the function, extend this function to another function f dash from f dash in 0, 1 in the closed interval. So whenever we extend this function continuously to another function say f dash, and then we will say that this f dash is continuous on 0, 1 closed interval. It is compact, therefore this function will be what? Uniformly continuous, right? Now, and the restriction of this function on this set is precisely f, and in this case, therefore we will able to say that this function f is uniformly continuous, in fact, right? So now we have to define, means using this f, we have to define another function say g from 0, 1 to r. For defining this g, we will use this monotonicity argument. I am saying again that you cannot extend this kind of see, this kind of function may not be extended always, but here you are given a condition that it is monotone and bounded. So we can let's see how do we extend this function. Okay, so since f is monotone, I am assuming that so it will be either monotone increasing or monotone decreasing, right? So which one you want to assume? Decreasing or increasing?
Increasing.
Okay, monotone increasing, say, right? Then we say that if x and y belongs to 0, 1, then what can we say from here? Fx less than equal to fy, right? You also have two more quantities, small m and capital M. So small m should be here since it is infimum, and capital M should be there. Fine.
Yes, sir.
Now we are trying to extend this function. Actually, say this function is not defined in at the point 0 and or not at the point 1. Fine. So now let's see. You also know that this small m and capital M are limit points of its image. Now we are our aim is to prove that limit x goes to 0 plus fx equals to m, and limit x goes to 1 minus fx is equal to capital M. Fine. And then you will able to prove that this function is in fact a continuous function, right? Can you prove it now? Can you check whether this limit say yeah, this is fine. So this limit 0 plus fx is equal to m, 1 minus fx is equal to capital M, right? Now you define another function g from 0, 1 to r by g of 0 is equal to small m, g of x equal to fx for 0 less than x less than 1, and g of 1 is equal to capital M, right? So whenever you define this in the g function in this way, you will see that the situation occur. G is means the left limit and left hand limit and right hand limit all exist and same as, and are equal whenever the values are lies between 0 and 1. At the point 0, the function is right continuous. At the point 1, the function is left continuous, right? And therefore, this property we can say that the function g is continuous over this closed and bounded interval 0, 1, right? And whenever this is continuous in 0, 1 and it is compact, compactness will give you that this function is uniformly continuous. And so now you have a uniformly continuous function, and if you take the restriction on any set, then this function will again be uniformly continuous. That's all. That is the argument. So the main fact is you have to extend this function from 0, 1 open interval to this closed interval. Okay. And by using this kind of arguments, again, you need to verify this one. So limit x tends to 0 plus fx and limit x tends to 0 minus fx, whether they exist or not. So should we do this? Okay. Shall I prove this too or leave it for you? Can you verify this too? Or I shall prove one and leave it leave the other for you.
Yes, sir. Prove one.
Okay, fine. Now you should supply me the arguments I needed. Okay, I will ask you and you tell me. So see, this is okay. Let me prove this one. See, M is the infimum, right? Infimum of f or infimum of fx, whatever. You can say this one. Now, so for to prove this one, what we need to prove? For epsilon greater than 0, there exists delta greater than 0 such that what 0 plus means whenever x belongs to 0 comma delta plus 0, let's say fx minus m should be less than epsilon, right? This is the definition of right
Yes.
hand limit, right? Yes. So now we will find out, chosen epsilon, we will find out some delta. Tell me one thing, if one epsilon is given from the definition of infimum, what do you say? What you can say about infimum? If we take say m plus epsilon, will it be an infimum?
No, sir.
No.
Then so m minus epsilon is not an infimum, right? Then what happens
Yes,
then?
there is an element.
There exists an element. Say what? Say delta, right? Say delta. Actually, I want to use this delta. You can say even x also. X fine. X not. Fixed element x not. Such that this m less than equal to fx not strictly
Less
less
than
than
m plus epsilon.
m plus epsilon, right? Now again, we have one x naught belongs to where 0, 1, right? Oh, I do not have that much space. Okay, I'll do here using a different color. Okay, so x naught belongs to 0, 1. Say this is your 0, this is your 1, and somewhere x naught is here. Now we take another any point, so this is your x naught. Okay. Now take a point x from here. Then what can you say about this? What can you say about fx?
Less than equal to fx naught.
Yes, exactly. Less than equal to fx naught, right? And so use it here. You can say m less than equal to fx less than equal to fx naught less than equal to m plus epsilon. That's mean if you take any point from here, from this neighborhood 0 comma x naught, then this will implies, and if you take x belongs to here, then m will less than equal to fx less than equal to m plus epsilon, right? And even you can say it is strictly less than m minus epsilon also. So this is strictly less than, right? Or less than equal. Anyway, so you can say that this fx minus m, what it is less than epsilon, right?
Yes, sir.
Whenever x is in this set, you have fx minus m less than epsilon. That is why I have chosen this x naught as delta here, because this x naught satisfies my situation, because this x naught is positive and you have positive x naught. Fine. So therefore, this limit exists. and equal to m, right? Now the second one is exercise for you. Okay, is it clear?
Yes, sir.
Yes,
Huh.
sir.
If not, you can tell me, because as sir told you, from compactness there will be 40% of weightage in your major exam. So you have to understand, or even you have to solve many problems also. Okay, you find, then we shall move to the next problem. Okay, fine. So if it is, if you have understood, then it is fine. We will move to problem number 3. So what does it say? Oh, it is this. Okay, so what does this problem say? So X, you have a topological space X, and then X is compact if and only if every collection of closed set in X. So you have a collection of closed set C or script C having finite intersection property has a non-empty intersection. So what do you mean by finite intersection property? Say you have a collection of set, say U alpha. Alpha belongs to some index set. This has finite intersection property. What do you mean by that? So finite intersection property? Anyone? If you know? Piyush?
Sir, if every sub collection have finite intersection. Sorry, non-empty intersection.
Every finite subcollection has non-empty intersection, right? Fine. Yes, yes. So if you take a finite subcollection, you're in if you take a finite subset of this one, or you can say um, intersection of finite collection of elements of C is non-empty. Basically, if you take any finite subcollection of this one, it has to be non-empty. Fine. Now the question says if X is compact, then if you take any this such collection of closed sets which has finite intersection property, then their intersection should be non-empty. I can say this, yeah. So their intersections should be non-empty, and conversely means if for any collection of a closed set having this property such that this condition holds, then the space is compact. So can you please try this problem? Tell me whether you understood the problem or not. About the finite intersection and even the problem. So have you got the problem? What does it ask?
Yes, sir.
Then you can try. So any argument? Okay. So for the forward part, so let X be compact. And say C be a collection of closed sets having finite intersection property. Okay. So you have to, what you have to prove? You have to prove that intersection V belongs to this C, V is non-empty. To prove this one. What happens if this is empty? So suppose intersection V, this is very easy. You just take this to be empty. Then what can you say? This
Com-
implies
we take complement of both sides.
yes. V belongs to C. This V, its complement will be X, right?
Yes, sorry, X.
X. So this implies union of V belongs to this C. V complement is X. What is V complement? It is
Open.
open.
Yes,
And therefore, if you take this collection V complement such that V belongs to C, if you take this as your set, this will be an what?
open cover. Open
Open
cover of
cover.
X.
Yes, this
And
is
it is compact.
an open cover of X. Now since X is compact, it has finite subcover. Say there is some V1, V2 up to say Vn such that what? This
It's equal to
X
n of
equal
V
to
X.
union of I equal to say 1 to n Vi complement, right? Now you take the complement of this one. This implies phi is equal to I equal to 1 to n Vi. Fine?
Yes, sir.
By which law? De Morgan's, right? And therefore, there is a finite collection, say V1 up to Vn, whose intersection is empty, contradicting the hypothesis that the C has finite intersection property. Because for a C having finite intersection property, if you take any subcollection of finite elements, you will see their intersection should be non-empty. But here you found one finite collection whose intersection is empty. Now we prove the converse. So now let's prove the converse. So what? To prove that if for any collection of closed sets having finite intersection property, the intersection is non-empty, then the space X has to be compact. So to prove compact, by we shall start with say an open cover. So let U equal to say U alpha. Alpha belongs to lambda. B an open cover of X. Okay, this is an open cover. Fine. You have to find out a finite means finite collection of this one, which also covers X. Right. So this is an open cover means this implies X equal to
Union.
union alpha belongs to lambda U alpha, right? And this will implies intersection alpha belongs to lambda U alpha complement is what?
Phi.
Phi. So this is a collection of closed sets such that their intersection is empty. Therefore what? By the hypothesis, see if we take this collection, say U dash of say U alpha complement such that alpha belongs to lambda. Okay, we consider this collection, collection of closed set. Now, if this collection has finite intersection property, then their intersection should be non-empty, right? By the hypothesis.
Yes, sir.
I'm repeating again. If this collection has the finite intersection property, then by our hypothesis to prove the reverse, this intersection of all the elements should be non-empty. But here we have, for this collection, we have the intersection is empty. Therefore, this collection does not have the finite intersection property, right? And that's mean, so this collection has it does not satisfy the finite intersection property. So what does it mean? This means there exists a finite collection of elements or finite number of elements such that whose intersection is empty, right? There exists a finite number of elements say U alpha 1 complement, U alpha 2 complement up to U alpha n complement such that intersection I equal to 1 to n U alpha I complement is empty. Now can you complete the argument? Can you complete the proof now? What does it implies?
Take complement both side.
So from here its complement is x, right? X equal to union I equal to 1 to n U alpha I, right? Because we just take complement over both sides. Let me use the blue color. We just take now complement here. If we take the complement here, you have to take the complement here. The complement means nothing but this one. Therefore, this collection has a finite sub collection which covers X. Therefore, X is compact, right? Is it clear? This is a nice argument and it is important. Sometimes this argument is important and some people use this argument to prove something is compact when they need. Okay, so this is also important, like you have tube lemma, you have Pusting lemma. So this is also similar kind of things. Means one of the important argument using finite intersection property. Fine.
Sir,
Yes.
sir, please repeat the converse part.
Sure. You should tell me. Okay. So is it clear that their intersection is empty? Intersection of U alpha complement is empty because
Yes, sir.
it is an open cover and therefore X is equal to the union. If you just take the complement here, then you will get this one. Now you see this is a collection. Each U alpha complement is a closed set. So if you take the collection of all U alpha complement where U alpha belongs to this U, what you can say, this is a collection of closed set. This collection of closed set such that the intersection is empty. Means if we take the intersection of all the elements present in U dash, it is empty. Now, if this collection has the finite intersection property, means if for all finite subsets of this U dash, the intersection is non-empty, then we have assumed that this all closed collection has a finite intersection property. Means we have assumed first this one. We have assumed that suppose our hypothesis for the converse is Suppose every collection of closed sets in X having finite intersection property has a non-empty intersection. Now, is it clear? Understand the hypothesis for the converse part first. The hypothesis is, if we take any collection of closed set which has the finite intersection property, then their intersection is non-empty. Means if we take this intersection, it has to be non-empty. Fine. Now you see, for this collection, if this collection has finite intersection property, then by the hypothesis, it has to be non-empty, right? By the hypothesis, this has to be non-empty. But here we have this intersection is empty. Therefore, what we can say that this collection does not have the finite intersection property. Fine. So this collection does not have finite intersection property means there is some finite collection of elements, say this kind of elements finite in number, such that the intersection is empty. Now this intersection is empty, you just take the complement, you find out that the right hand side, the complement of empty set is X, and this complement by the De Morgan's law from set theory, you have this complement, whole complement is union of complement complements. Therefore, this set actually. So you have X as union of UIs. Is it clear?
Yes, sir, clear now.
Fine. So if it is not clear, tell me. I will explain again. No problem. Okay. So problem number 4 now. Okay. So consider a closed, continuous, and surjective function. Okay. So you had something closed, continuous, and surjective function. You have studied somewhere earlier, right? Before your minor. What kind of function was that? What kind of map was that?
Quotient map.
Yes, quotient map. So it is a quotient map, right? A closed, continuous map, surjection map, and closed map. It's a quotient map, right? We can say. Can we say it is a quotient map? Yes, no.
Yes, sir.
Closed maps are quotient map. Yes. Anyway, now here things are different. So you have to consider a closed, continuous, and surjective function f between two topological spaces, say x and y. Okay, x and y are given two topological spaces such that f inverse singleton is compact. Okay. So this singleton set is compact for each y, so that y itself is compact. So that here is a full stop. So that if y is compact, then x is compact. Think about this problem. Okay, this is, I want to give it an exercise. First, think about it. It may need a half an hour to solve or to think and then solve. It is for an exercise for you. You try to solve this one. If you are able to solve, then fine. If you are not, then you can just put me a message in MS Team. I'll send you the solution. There's nothing much on this one, but you have to think about this problem. Okay, fine. Using compactness of y, you have to prove the compactness of x. Okay. Shall I skip? Do you want solution now?
No, sir.
Okay.
Yes, sir,
Fine.
we will try.
Sure. Fine. Okay. Now you know RK. Now tell me what is RK. Tell me what is RK. I taught you in the first tutorial session. What is RK? Again, I am saying K topology. Okay. It's called K topology on R. Tell me what is RK?
Sir, close A, comma, open B minus 1 by n belong to n belong to n. Yes.
What? Closed A,
Yes, sir. Open B.
open B, then
And minus K.
minus K. Is it?
Sir, open A comma B minus
Open
A
A
union
comma B minus K, right?
union. Yes.
Such that
K equal
what?
to 1.
A comma B, I will define A comma B belongs to R with A strictly less than B, and union what? You also have one more collection.
A
What?
comma B.
Yeah,
A
A
comma
comma
B.
B, such that A less than B. Where? What is K here? Your K is 1 by N, right? Right? So if you take this collection, the topology generated by B is called K topology. Or actually the basic open sets are of this form. Let's say means open AB and A comma B minus K, this kind of forms. Let me take it as CD. Okay, C comma D, otherwise you will get confused. So C less than D. Okay, and CD belongs to R. Okay. So this collection actually these are the basic open sets. AB minus K of this form and of this form. Okay, and so any open set will be the arbitrary union of this kind of basic open sets. This is the topology RK. Now, so you have to prove that whether 0, 1 is compact or not. Okay, I've given that this is not compact. Okay, so you have to prove that this is not compact. So that so you need to find out an open cover which has no finite subcover. Let me open cover. Audible? Am I audible? There was some internet issue.
Yes, audible.
Yes,
Huh,
sir.
huh, Fine. So can you give me an open cover of this set? Okay, so first take say U equal, okay. Let's say U is equal to what, minus half to say 3 by 2 minus K. Is this open? Is it open?
Yes, sir.
Yes.
It is open, right? And for each M, so and by this open set you have covered the interval 0, 1 except the point, except the set subset K, right? You have covered everything except this K, because this is in fact 0, 1 is a subset of the first set, but from the first set you have removed K. So in fact you have covered 0, 1 except this set, this countable set, right? Now we will produce a cover of this set, and so that we will not have any finite subcover. So for so what are the elements of K? Which are of the form 1 by M, right? For this element, consider, and of course for M greater than 1. Okay. Consider this set Um to be 1 by M minus 1 by M plus 1. Right? Comma 1 by m minus this plus 1 by m minus 1 by m plus 1. Oh, this is not right. Actually, what? Actually, you first look at the picture and try to understand. So this is say your 0 and this is your 1. Okay. And you have here you have half, here you have 1/3, here you have 1/4, and then you have 1/5 somewhere here, and then you have 1/6, 1/7, 1/8, 1/9, 1/10, like this. Okay. So and in this way. So now let us zoom this picture somewhere here. So you have what you have here? You have say have somewhere 1 by m, and here somewhere you have 1 by m plus 1, and somewhere here you have 1 by m minus 1, right? Right?
Yes, sir.
Huh. So now can you tell me which distance is more? This distance or this distance?
Sir, second.
Yeah, this distance is more than this distance, right? Right? Now, uh, so and what is the distance between 1 by m and 1 by m minus 1? This is 1 by m minus 1 by m minus 1, right? This is the distance. This is your a. If it's a and it's your b, then the distance is b minus a, right? And this is your say c. Now you consider this neighborhood. Consider a neighborhood about 1 by m of this form, here to up to here. So you have a length a minus b. So you have here 1 by m. Consider 1 by m minus b minus a and 1 by m plus b minus a. Actually, you have to take, you have here a 1 by m, you have here 1 by m plus 1, and somewhere here you have 1 by m minus 1. You will consider a neighborhood of this length. Let me use black. Neighborhood of this length around 1 by m, right? And you say consider it as um. Okay, clear? So take a neighborhood, or say take a stake. You have as, let me write it precisely, 1 by m minus, what is this length? What is the length? 1 by m minus 1 by m plus 1, right? This length, the neighborhood around 1 by m, comma 1 by m plus 1 by m minus 1 by m plus 1. How do you write an epsilon neighborhood of a point? This is x minus epsilon, comma x plus epsilon, right? Epsilon neighborhood. Yes.
Yes, sir.
This is your epsilon neighborhood around x. Now take epsilon as this length, and this length is 1 by m minus 1. Take epsilon as 1 by m minus 1 by m plus 1, and consider the epsilon neighborhood around 1 by m. You see, and the name is as um. Then you will see, you take this collection um such that M belongs to N. To consider this collection, you will see that this union union the set the collection U, this is an open cover of 0, 1, 0, 1 close interval, but it has no finite subcover. Okay. First tell me whether the construction is clear. If the construction is clear, then rest is nothing. Is it clear?
Yes, sir.
If it is not clear, I will explain. Others, please. If you can understand the construction, you will easily prove the rest things. This is the important. This is important one. So how do we construct this sets UM? I will ask one by one. What about Piyush?
So not exactly.
Not. Then you should tell me, right? What about Sita Basu?
Yes, sir. Clear.
So my
Clear.
question is that sir, zero open and close one is open in this architopology. Open zero, close one.
Open 0, closed 1. No,
Is it
right? It should not be open, right?
okay? Okay. Okay.
What is its complement? Its complement is uh, uh, okay. Yeah, it is not open. Can easily verify. 0 open 0 closed 1 is not open. Okay, Sita also is clear. What about Bhavana Agrawal?
Yes, sir.
Clear. Arpit?
Yes, sir, clear.
Clear. Sanjuvala?
Yes, sir. Clear.
Bharti? Bharti Gupta?
So I got till the point you have defined UM.
You have got the point. I have defined UM. Okay, fine. If you have got this one, you will be easily you can easily solve the rest things. What about Devika?
Yes, sir.
Uh, have you got the construction?
Yes, sir.
Fine. Then I will explain for Piyush. Look at here. Okay, let me use this space. You have the set 0, 1, right? Please understand carefully. This is not that much difficult. So you have this set 0, 1. This is your point half. So somewhere here the point 1/3. Somewhere here the point is 1/4, and then 1/5, then 1/6, and so on, right? Now you choose somewhere in between the point 1 by m. Okay, and let us try to understand the point 1 by m plus 1 in the left side of 1 by m, and the point 1 by m minus 1 in the right side of 1 by m. Okay, so now just take the neighborhood of 1 by m. So or the neighbors of 1 by m. So say suppose here is your 1 by m. Here is your 1 by m plus 1. And here is your 1 by m minus 1. And as they said that this length will be smaller than this length. Right? It is nothing like just the length is 1 by m minus 1 by m plus 1 is less than 1 by m minus 1 minus 1 by m. So that's all. This is the argument. Now we take the neighborhood around 1 by m of length this length. So this is your length, and we take a neighborhood around 1 by m of length 1 by m minus 1 by m plus 1. This will be of this form, this one and somewhere here. We will consider this open set and call it UM, nothing else. So this UM actually contains this 1 by m actually. In fact, if you take K intersection UM, it is actually 1 by m singleton set. That's all. This will be your open sets. Now you see these are open, and we have taken another big open set, say U, where it is this one, right? U covers the entire 0, 1 except K. Okay, so you have U. If you take the collection, say beta as U union these U M's, M belongs to N. In fact, you can cover this set. M belongs to N. Then this will have no finite subcover. And why it does not have any finite subcover? I'm saying again. Let's see. Say suppose U, comma UM1 and up to UMR. If this if you take any finite sub collection, now you take the maximum of M, say M is equal to, or say M0 equal to maximum of M1 up to Mn or Mr, you will see that 1 by M0 belongs to 0, 1, right? But 1 by M0 does, or sorry, 1 by M0 plus 1 or 2, say 2, but 1 by M0 plus 2, it means if you take the bigger than, so some the integer after 1 by, positive integers after M0, you will see that the this fraction will not be in, this does not belongs to this union. So union of M or I equal to 1 to R, say UMR union U. So this does not belong to here. That is why it is not, it does not have any finite subcover. Fine.
Yes, sir.
Piyush, you had
Yes, sir.
doubt.
Yes, sir. Clear.
Huh. Then fine. Okay. So actually, I do not want to remove this thing. Okay. Tell me one thing. Can you solve this one? Every if X is compact, then every infinite subset has a limit point. Of course, in a topological space. Limit point means the elements in the derived set, or in other words, we call X is a limit point if for any open set U around X, U minus X intersection A is non-empty, means U contains some element of A other than X. Okay, that's what called limit point. So can you prove this one?
Yes, sir.
Yes, fine.
Yes.
Good. So this is fine. Is the converse true? So for the converse, think about this one. Say X is as X as N, Y as two element set, say A comma B. Okay, and say define the topology Y, say sigma consists of, or sigma, define topology on Y as sigma S phi comma Y, means the indiscrete topology Y, and consider X cross Y, or in fact you can take N cross Y. N is from subspace topology from R. Okay, you can say this, in this set you will see that every subset has a limit point. In fact, every singleton set also has limit point, but you will see that this is not a compact set, because you will see that if we take N, what, N comma A union N comma B. Okay, this two element set will be an open cover of this one, but it does not have any finite subcover. Actually, what, the singleton sets are open in here, right? X. So if you take any N, then N cross Y will be an open cover of, sorry, N cross Y will be open in this set X cross Y, right?
Yes,
So
sir.
this set N belongs to N will be an open cover of this set N cross Y, right? But it has no finite subcover, therefore it is not compact. But you will try to see that the in this set Means if we take n cross y or say x cross y, then every subset has a limit point. Okay, fine. Now this problem, a T1 space is countably compact if and only if every infinite subset has a limit point. It is the upper version of the above problem. It is higher dimensional version. It is not higher dimension. It is some weak kind of things, right? Countably compact, right? Every infinite subset, but one way is obvious, right? From the last result, which one? X is compact, then every infinite subset has a limit point. No, it's not obvious. X is countably compact if and only if every infinite subset has a limit point. Fine. Should I stop or I shall solve this problem? Huh? What?
करवा दीजिए सर ये वाला.
हाँ करवा दो, ठीक है. Oh. Anyway, so first let's prove the forward. So let X is countably compact. Let X be compact and say A an infinite set. Okay. We have to prove that A has a limit point. So suppose A dash is empty. Fine. A dash is empty implies. Tell me one thing. If we have an uncountable say U an uncountable set, okay. Can we say that you always have a countable subset?
Yes, sir.
We can say it has a countable subset, right? So U is uncountable implies there exists some B subset of U such that B is countable. Also, suppose B dash is non-empty, means suppose say W belongs to B dash, means W is a limit point of B. Can we say W belongs to U dash?
Yes, sir.
Yes, sir.
Because this dash, right? Anyway, so if we now look at this one, we have assumed that an infinite set A dash is we have assumed that A is an infinite set. We also assume that it has no limit point. Okay, so and it is given that the space is countably compact. So you have to prove that if it does not have a limit point, then it is not compact. Okay, we will prove by contradiction. Suppose this is holds for any subset. क्या हो गया? इसका हाँ. You see, if we can work with the countable sets only, that every countable infinite set has no limit point, then it will be fine. Because once you able to do this one, actually our aim is to construct. Okay, let me tell it precisely. Suppose you have an uncountable set or you have any set A, infinite set, and suppose A that is empty. Fine. Then from here, what you can say? You can say What?
A is closed.
A is closed. Actually, I want a countable subcover. Okay. Is a closed set. Hmm. Okay.
So you
Fine.
are assuming A is countable set.
In fact, I have started with infinite set. Let's see if we are able to reduce the fact from uncountable to countable. Actually, this countably compact means if every countable cover has a finite subcover, right? So
Then
and
sir, it will be जी sir take you take open cover x minus ai where
uh,
I greater or equal to n.
I greater equal to n, then
Yes sir. Then union of un covers whole x.
union of a covers whole x. Yes, then
So वहां से प्रूव कर पाएंगे कि इसके पास मतलब फाइनाइट सपोर्ट नहीं होगा बट वी हैव टू अज्यूम दैट इट इज काउंटेबली कॉम्पैक्ट व्हिच इज अ
uh,
कॉन्ट्रडिक्शन.
fine, fine, fine. But I want something more. Actually, any uncountable set से मैं countable set concept करना चाहता हूँ. तुम्हारा आर्गुमेंट ठीक है पीयूष?
सर एक्चुअली ये है यहाँ पे हमें गिवन हमने माना है कि a डैश इक्वल टू 5 तो हमने ये बोल
हाँ
दिया कि a इज क्लोज्ड एंड हम सर ये भी बोलना चाह रहे हैं कि एवरी सबसेट ऑफ a इज आल्सो क्लोज.
हाँ हाँ
सो वहां से हम बोल देंगे कि ए काउंटेबल है तो इसकी कोई इन्यूमरेशन एग्जिस्ट करेगी a1 a2 डॉट
हाँ
an डॉट
हाँ
डॉट.
हाँ हाँ, वो तो काउंटेबल के लिए हो गया. एक्चुअली वो तो ठीक है, काउंटेबल के लिए आर्गुमेंट ठीक है, मिल गया जो तुम बोल रहे हो, लेकिन जब अनकाउंटेबल है ना, ये अनकाउंटेबल से मैं कुछ करना चाहता हूँ. समझ रहे हो? हाँ, तुम्हारा आर्गुमेंट यूज करके ही जो तुम बोल रहे हो ना, एनी सबसेट विल बी क्लोज्ड. हाँ, उसको यूज करके ही करूंगा. Okay, so let's use his argument. He's saying that if we take any subset A, then this set will again be closed, right? Piyush, you are saying this one?
Yes sir, yes sir.
Because its derived set is empty. In fact, so for if you take any subset, then its derived set will be empty. So if even if we have an uncountable set, an uncountable set will always have a countable subset. Say it is B, or we can say it is A. So say A is a countable subset. So now even we have a uncountable set, we will work with this countable set. Fine. Now for this A, if you take an element A from there, this A is not in A dash because A dash is empty, right? So this, since this is not in A dash, so there exists an open set UA, or you can say there exists a neighborhood UA of A such that UA intersection A is only a singleton set, right? Because the A is not in the derived set. Now you consider this collection. So yeah, on the other hand, since A is closed, you have X minus A is open, right? So X minus A, now you consider this collection, say X minus A union this UA such that A belongs to A. You consider this collection, say our A is countable, therefore this set is countable. Now countable set union a finite set is countable. So U is a countable open cover of X, right? Now since X, now if X is countably compact, this will imply it has a finite subcover. Every countable cover has a finite subcover. The definition of countably compact set. So this will imply that there exist elements say A1, A2 up to AN such that your X is subset of X minus A, this is capital A, X minus A union I equal to 1 to n u a I, right? But this set is decision from A, and therefore A will be subset of union I equal to 1 to n uai, right? But you see each uai contains exactly one element of A, and A is subset of the finite this union, so this implies A is finite. Fine, but we have assumed that A is countably infinite. So A is an infinite set. We have assumed, in fact, it is a countably infinite, and therefore it is a contradiction, right? So therefore this contradicts that A is infinite. Fine. Clear? I have not used the T1 argument here. T1 argument will be used for the converse part.
Yes, sir.
Okay. Others, please response if it is clear. Okay, so I assume that it is clear. Now for the converse part, we will assume that every let every infinite subset has a limit point. Okay. So let every infinite subset has a limit point. We will prove that it is compact. Or no, not compact. We have to prove that it is countably
Completely
compact, right?
compact.
Yeah, countably compact. Thank you. So for that, let say u alpha, not alpha. We can take un. N belongs to n. Be a countable open cover. Okay. Open cover of X. And suppose it has no finite subcover. Suppose this U, or say this set U has, so this is our U, no finite subcover. Okay, so since it has no finite subcover, what we can say, you take U1, one element U1 from this U. So if you take an element, then of course, since it has no finite subcover, then of course X is not equal to U1, right? X cannot be U1 itself because it has no finite subcover. Because if X equal to U1, then your U1 singleton set will be a finite subcover. So and this implies, so there exists some element in X minus U1. So let X1 belongs to X minus U1. Actually, our aim is to construct an infinite set which has no limit point. Okay. Not only that, we will construct an infinite set, or see, we will give a contradiction. Okay, first. So let x1 belongs to x minus u1. Fine. Now you see this collection, this u all n, such that n belongs to n is an open cover, right? Actually, it's a covering, and x belongs to x1 belongs to x. So this implies there exists something, some elements here. There is some open set, say um, which contains this x1. So suppose there exists some n2 belongs to n such that, say, let's say this element is n1. Okay, we are giving, we are just renaming this set as un1, n2 such that x1 belongs to un2, right? Now you consider the set Vn2 is equal to I equal to 1 to n2 un or ui. You consider this set. This set again is a finite union of elements from this set, this collection, right? And since it has no finite subcover, this cannot be again X. This will be a proper subset of X, right? Now you see again X1 and X2 both belongs to this set. But this is which is a proper subset of X. Therefore, what you can say? There exists some X3 belongs to this X minus, say, Vn2 or say Vn2. And since X3 is in here, so this will imply one second, I made a mistake here. X1, this is X1 here. We will take X2 only. Okay, so X2 belongs to X minus Vn2. So, and since X2 is again in X, then by the hypothesis this is an open cover, we will have some, there exists some N3 such that X2 belongs to UN3. You consider Vn3 as union I equal to 1 to n3 ui. You will again, by the same argument, you will see that this set is not the whole X. So there will be something, say X3 belongs to this X minus Vn3. Ultimately, you are doing this kind of arguments, we will find first one a sequence Xn. Xn subset of X n equal to 1 to infinity such that the elements are distinct. Xn not equal to Xm. Right? For n not equal to m, the second condition will be this Xi will belongs to Vn I minus 1, right? Vn I minus 1 or Vn I plus 1, which one? X1 belongs to Vn2, X2 belongs to Vn3. It will be I plus 1. Xi belongs to Vn I plus 1. Okay. By this. So now you have an infinite set, this one. So what we have assumed is that every infinite subset has a limit point, right? So therefore this set also has a limit point. By the hypothesis, this set Xn, this sequence has a limit point. In fact, we can say it converges some point. Okay, say X. Now since also from here our third hypothesis will be, or our third conclusion will be, this union of Vni is same as union of ui, and this is X. But actually we are taking Vn3 as union up to n3, I equal to 1 to n3, and therefore this Vn3 will be the union of this one, and if you go further and further, you will see that this Vn, their union is same as the union of Ui, and this union is X. Fine. Now we assume that, so by the hypothesis, this has a limit point, and this limit point, say it is X, and this X will enable U. So again, this X will be in some Vk by this hypothesis. Fine. So once you have this Vk, and since X, it is a limit point, so this Vk will contain some element, right? Vk, this will imply there exists some xm belongs to Vk and xm not equal to X, right? Yes. Xm not equal to X. So this, using this kind of xm, you now consider you have Vk, you have xm. Now you see this xm belongs to Vm, the way we have constructed. Also the space is T1. So you can take this set now. Say Vk intersection xm complement. Right? Now Vk contains X, xm is not equal to X, so this is again an open set. Fine. This is an open set containing X. Fine. Is it become complicated now? Piyush, are you feeling complicated this problem?
Yes, sir, too much.
Too much complicated. Okay. Then it will be easier for you if I write the solution and send it. I think it will be easier because here is nothing that much to understand, but I'm explaining, and that's why it's become complicated. Actually, this construction, there are so many constructions. Here is Vk, and taking the sequences, and then taking this kind of constructions. Too much
सर मैंने
constructions.
एक्सेप्ट किया है सर, वो बताऊं?
हाँ, बताओ.
तो जैसे आपने वहाँ पे चूज किया था ना x1 x2 डॉट डॉट x3 इस टाइप से,
हाँ हाँ
तो वैसे मैंने मतलब एक सेट बना लिया a1
हाँ
टू से an बिलोंग टू नेचुरल नंबर।
हाँ.
तो हमने इसको प्रूव किया कि ये इनफाइनाइट सेट है।
अच्छा अच्छा, कैसे कैसे प्रूफ
मतलब
किया?
सपोज इट इज फाइनाइट,
हाँ, फाइनाइट.
then it is covered by some finite subset of open cover.
फाइनाइट सबसेट ओपन कवर क्यों?
सर अगर मान लो फाइनाइट है तो फिर वो फाइनाइट सेट से तो कवर हो जाएगा ना, मतलब उससे किसी भी एक सेट से कोई।
हाँ 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 हाँ, कवर हो जाएगा. हाँ, हो जाएगा. देन
तो फिर मैंने बोल दिया कि ए इज इनफाइनाइट सेट। अब हमें ये प्रूव करना है कि इट हैज नो लिमिट पॉइंट।
हाँ
अगर ये प्रूव कर दिया तो हम विच इज अ कॉन्ट्रडिक्शन।
हाँ,
तो
प्रूफ
फिर
किया हो?
हेलो सर, क्या?
प्रूफ किए हो?
हाँ सर, प्रूव तो किया मैंने।
अच्छा, ठीक है ठीक है ठीक है. तो तुम एक काम करो, तुम्हारा वो जो प्रूफ किया हो ना, वो मुझे फोटो खींच के भेज देना.
यस सर।
ठीक है, मैं वो
आप
वेरीफाई कर लूंगा, और मैं इसको सॉल्व करके जो कॉन्वर्स है, फॉरवर्ड तो हो ही गया है, तो कॉन्वर्स मैं अच्छे से लिख के तुमको भेज दूंगा. ठीक है,
ओके ओके
कहाँ पे भेजू? मैं वो अपलोड कर दूंगा, जो क्लास मटेरियल्स है जहाँ पे मैं अपलोड करता हूँ, उसमें कर दूंगा. ठीक है,
ओके
बाय
सर।
टुडे और बाय टुमारो.
ओके सर।
Actually, I did something, some rough kind of things. I was looking at that, but I think it becomes complicated to you. So it's better to skip and send you the solution. Okay, so you will understand. If you get trouble at somewhere, please ask me in the next session. Okay. Okay then, we'll end the session.